Okay, so this question is causing quite a few problems. I'm going to go through it a little bit here for you now. So first off, we're given that we've got 4,000 students and their tests should be normally distributed with a mean of 100 and a standard deviation of 10. This is the normal distribution for an IQ test. The psychologist wishes to test to see whether the students are normally distributed. So we're going to do a chi-squared goodness of fit test on this one. The first thing we need to do is copy and complete the table and show how you arrive at your answers. So this is a normal distribution, and you need to calculate what the expected frequencies are. So we're told that X is normally distributed with a mean of 100 and a standard deviation of 10. So that would be a variance of 100, or 10 squared. We need to calculate the probability for these three events here. So the first thing we need to do is say that the probability that a student selected at random will have an IQ between 80.5 and 90.5. We use our calculator for that. So we need menu, probability, distributions, normal distribution. We're going to go from 80.5 to 90.5 with a mean of 100 and a standard deviation of 10. This gives us approximately 0.145. We need to find the expectation that a student selected at random will be in this interval. So we take this probability, we take the exact value, and we multiply it by 4,000, because there's 4,000 students. So it's about 15% likelihood that a student picked at random is in this interval. So if we multiply that 14% by 4,000, this will be how many students we would expect to find in this category. And this is going to be equal to 582. So this one is 582. We need to repeat that calculation for the other intervals. So the expectation that it's going to be between 90.5 and 105 is going to be equal to menu, probability, distributions, normal CDF, 90.5, 100.5, 110. Times that one by 4,000. So this is 0.349. 0.349 times 4,000, which is going to give us 1396. 1396. 396. Lastly, do the last one. Oops, missed it. Okay, missing. Menu 552. And we need a 100.5 to 110.5. And this is 10 times that by 4,000. So the expectation that they'll be between 100.5 and 110.5 is 0.333 times 4,000, which is equal to 133. 1333. I'm going to round that to an integer value. I'm not rounding it to three significant figures. That would be 130. I want it to be a little bit more precise than that, so I'm going to write it to the nearest integer. That gives me 1333. So now that's part A. I'm going to answer part B now. So the first thing I notice for part B is I need to test the hypothesis. So she's testing to see whether these are normally distributed. Those are expected frequencies and the observed frequencies. But one of the problems we encounter first is that the expected frequency here is 4. You cannot have an expected frequency in a chi-squared test, any of the two types of chi-squared test, that is less than 5. So what we have to do is we have to adjust these numbers. We have to contract these two rows into a single row. And then this one's going to be 84, and this one's going to be 80. So now if we look at the number of degrees of freedom, we've got 1, 2, 3, 4, 5, 6, 7 rows. So the degrees of freedom is going to be 6 for this test. So first off, we need a null hypothesis. The students are normally distributed. And the alternative hypothesis, the students are not normally distributed. Next, for this test, we need to calculate the degrees of freedom, which is the number of rows minus 1. So that's 7 minus 1, 6. Now we need to enter the data into our calculator. Oh, sorry, let me just show what I wrote there. Looking at my iPad. So, show what I wrote there. All right, let's do the test. We need to add a page list. So I've got my observed and my expected. Type the information in. 20, 90, 575, 1282, 1450, 499, and 84. 696, 582, 1396, 1333, 507, 80. We're going to do a stat test. We want the chi-squared goodness of fit test. We need the observed list, the expected list, and the degrees of freedom. So this gives us a chi-squared calc value equal to 53.0 and a p-value. Now look on the p-value. Notice this bit here at the end. Some of you forget to read this part and just ignore it a lot and get your answers very wrong. So this means the p-value is 1.16 times 10 to the minus 9. That's very, very small. That's very, very small. If you want to see how that looks as an expansion, we can get the p-value here. That's the p-value. And if you're trying to see it, press document 7.2 and go down and stick it to fix as many decimal places as possible. Press enter on that one, and then you can see it. We've got 3, 6, 7, 8 zeros. Okay. So to make our conclusion, we can compare it to the critical value, but in this question, the critical value is not given. If you're finding the critical value on this one, I'd like to know how you're finding it. You can search for the critical values online, but typically in an exam you would be given the critical value. As we're not given the critical value, we're going to have to use the p-value. So I need to always put an inequality. Any of your hypothesis testings always have to have an inequality in the conclusion. So 1.16 times 10 to the minus 9 is a lot less than 0.05, which is the significance level. This implies the p-value is less than the significance level. If the p is low, reject the whole. Oh, sorry, let me pop that out of the way. So if the p is low, let me just zoom on this one a bit better for you. There we go. Sorry. If the p is low, reject the whole. There is sufficient evidence to reject the null hypothesis. So there is sufficient evidence that the students' IQs are not normally distributed. Okay, that's how to answer this question. Sorry, just neatening it up. Can't get across the bottom. All right, finished that. No, it's not.